Combinatorics and Algorithms for Quasi-Chain Graphs. This is a joint work with Bogdan Aleku, IST Satminas, and Dmitry Malyshev. Before I define the notion of quasi-chain graphs, let me first say a few words about chain graphs, which is a well-studied class of graphs. Let me say that a linear order of vertices is perfect if the neighborhoods of these vertices are nested, meaning they create a chain with respect to set inclusion. Then a chain graph is a bipartite graph in which the vertices in each part admit a perfect ordering. This is a typical example of a chain graph. This example is typical in the sense that if we denote a graph of this form with n vertices in each part by Bn, then it's not difficult to show that Bn is an n-universal chain graph, meaning it is a chain graph containing every n-vertex chain graph as an induced subgraph. Paul Erdős called graphs of this structure half-graphs because they have approximately the same number of edges and non-edges between the two parts of the bipartition. By the way, half-graphs are very important in model theory, but this is beyond the scope of this presentation. Chain graphs form a hereditary class, which means that this class is closed under taken induced subgraphs, and therefore they admit a characterization in terms of minimal forbidden induced subgraphs. In this terminology, the class of chain graphs can be characterized as a subclass of bipartite graphs containing no 2k2 as an induced subgraph. A 2k2 is the graph represented here. So, as you can see in this picture, chain graphs have very simple structure, and that's why they enjoy many nice properties. In particular, liquid is bounded in the class of chain graphs. Chain graphs are well quasi-ordered under induced subgraphs. Chain graphs admit an implicit representation. I will be talking about this issue a bit later. Actually, these graphs appeared in the literature under various names: chain graphs, difference graphs, and to the best of my knowledge, the name chain graphs was first used by Yannakakis. Now we move to quasi-chain graphs, and to define this notion, let me relax the chain property of the neighborhoods in the following way. We will say that a linear order of vertices is good if for any two vertices the vertex with the smaller index has at most one private neighbor with respect to the vertex with the larger index. Then a quasi-chain graph is a bipartite graph in which the vertices in each part admit a good order. This is also a hereditary class, and it is also admits a characterization in terms of minimal forbidden induced subgraphs. In this terminology, the class of quasi-chain graphs can be characterized as a subclass of bipartite graphs containing no induced copy of an unbalanced 2p3. 2p3 is the graph represented here. It is a disconnected graph, so it admits more than just one bipartition, and I will call the bipartition in which the centers of the two components belong to the same part an unbalanced 2p3. And throughout this presentation, 2p3 always means an unbalanced 2p3. It's not difficult to see that an unbalanced 2p3 is not a quasi-chain graph because the centers of the components don't admit a good ordering. On the other hand, if we are given a bipartite graph which is 2p3 free, then by ordering the vertices in each part in a non-decreasing order of their degrees, we obtain a good ordering. That's why a bipartite graph is a quasi-chain graph if and only if it is 2p3 free. This is not a new class of graphs. It was studied in the literature. I will mention some papers. But the new paper, the paper I'm presenting you now, is the first one which is devoted entirely to this class of graphs. That's why we decided to introduce a special name for graphs in this class, quasi-chain graphs. It's not difficult to see that quasi-chain graphs generalize chain graphs, because for chain graphs, the right-hand side of this inequality always equals 0. And this small difference between a 0 and a 1 changes the structure and the properties of graphs in the class dramatically. In particular, click width of quasi-chain graphs is unbounded, which was proved in this paper. And quasi-chain graphs are not well quasi-ordered under induced subgraphs, which was proved in this paper. What is interesting that in both papers we used the same construction to prove the results. In this construction, we deal with bipartite graphs whose vertices can be partitioned into 4 subsets, say A, B, C, and D, so that A and C induce a 1 regular graph, A and D induce a chain graph, B and C induce a chain graph, and B and D induce a complete bipartite graph. It's not difficult to see that any graph of this structure is a quasi-chain graph. Now, since A and D induce a chain graph, the vertices of A can be linearly ordered under inclusion of their neighborhoods within this chain graph. Similarly, the vertices of C can be linearly ordered under inclusion of their neighborhoods within the chain graph induced by B and C. And these two linear orders are consistent in this representation in the sense that the edges in A, between A and C, don't cross each other. However, depending on the two chain graphs between A and D and B and C, the edges between A and C may cross each other, in which case these edges can be viewed as the intersection diagram of a permutation. Any two linear orders define a permutation. And if the permutation graph corresponding to the permutation encoded by these edges has large click width, and we know that permutation graphs can have arbitrarily large click width, then this quasi-chain graph also has large click width. We also know that permutations contain infinite antichains, implying that quasi-chain graphs contain infinite antichains. In the new paper, in the paper I'm presenting now, we elaborated on this topic and established a bijection between the set of all permutations and a subset of colored quasi-chain graphs, such that two permutations are comparable with respect to the pattern containment relation, if and only if their images, quasi-chain graphs, are comparable with respect to the induced subgraph relation. By a colored bipartite graph, I mean a bipartite graph which is given together with a bipartition of its vertex set into two independent sets, say of black and white vertices. And when we talk about the induced subgraph relation of colored bipartite graphs, we assume that this relation respects the colors. This is a purely combinatorial result, but it has interesting algorithmic consequences. In particular, it helped us to prove that the induced subgraph isomorphism problem is NP-complete in the class of quasi-chain graph. The induced subgraph isomorphism problem deals with a couple of graphs, and we want to know whether one of them is an induced subgraph of the other. A related problem for permutations is known as pattern matching, where we are given two permutations and we want to determine if one of them contains the other as a pattern. This problem for permutations is known to be NP-complete, and with the bijection between permutations and quasi-chain graphs established in this theorem, the NP-completeness of the pattern matching problem implies almost immediately the NP-completeness of the induced subgraph isomorphism problem in the class of quasi-chain graphs. This result can be viewed as a negative result. And we also established a number of positive results. And all of them are based on a structural characterization of quasi-chain graphs that can be described as follows. First of all, let me denote the symmetric difference of two sets in this way. Now, given two graphs, G1 and G2 on the same vertex set, we define the symmetric difference of the two graphs to be the graph on the same vertex set in which the set of edges is the symmetric difference of the set of edges of G1 and the set of edges of G2. With this terminology and notation, the structure of quasi-chain graphs can be described as follows. If a bipartite graph G is a quasi-chain graph, then G is the symmetric difference of two graphs, Z and H, such that Z is a chain graph and H is a graph of vertex degree at most 2. Moreover, the edges of H can be split into two matchings. One of them has to be removed from our quasi-chain graphs and the other has to be inserted into our quasi-chain graph in order to transform it into a chain graph. Alternatively, we can obtain our quasi-chain graph from a chain graph by removing a matching, shown here by dotted edges, and inserting a matching, shown here by bold edges. I don't claim that every graph obtained in this way from a chain graph is a quasi-chain graph. What I claim is that any quasi-chain graph can be transformed from a chain graph in this way, and this transformation can be implemented in polynomial time. I mentioned already that we derived several positive results based on this structural characterization. The first of them deals with the notion of implicit representation of graphs. This notion was introduced by these three people, first in a stock paper, then this paper, an extended version of this paper appeared in the journal, Science Journal on Discrete Mathematics. It is interesting that the journal's website contains a typo in the title of the paper. Roughly, the idea of the implicit representation can be described as follows. A representation of an n-vertex graph G is implicit if it assigns to each vertex of the graph a binary code or a label of length big O of log n, so that the adjacency of two vertices is a function of their codes. Sometimes this is known as an adjacency labeling scheme, and sometimes the definition puts some restrictions on the function computing the adjacency. An upper bound on the length of each label implies an upper bound on the number of graphs in the classes admitting implicit representations. In particular, every class of graphs that admits an implicit representation contains at most this many labeled graphs. Whether every hereditary class containing this many labeled graphs admits an implicit representation is a big open question known as implicit representation conjecture. The word hereditary here is important because without this word, this conjecture is known to be false. This conjecture was verified for a variety of hereditary classes. In particular, it is known that the conjecture holds for interval graphs, permutation graphs, line graphs, planar graphs. It also holds for all hereditary classes of bounded vertex degree, of bounded click width, of bounded arboricity, and so on. And now we show that the conjecture also holds for quasi-chain graphs, which was an open question until recently. An upper bound on the number of labeled graphs in the class of quasi-chain graphs was shown by Peter Allen. Again, Peter did not use the terminology of quasi-chain graphs, but he studied all subclasses of bipartite graphs defined by a single forbidden bipartite induced subgraph, without giving names to these classes. And now we show that the class of quasi-chain graphs admits an implicit representation. For this, we develop a general tool which can be described in the following way. First of all, let me denote for a graph G, we denote by AG the adjacency matrix of G, and by AG of X, Y, we denote the element of the matrix corresponding to vertices X and Y. Now, given a Boolean function f of k variables and k graphs h1, hk on the same vertex set V as the graph G, we will say that G is an f function of the graphs h1, hk if for any two vertices x, y in the graph G, the adjacency of these two vertices can be computed in two steps by first computing their adjacencies in the k graphs h1, hk, and then by applying the function f to determine their adjacency in the graph G. With this terminology and notation, one can easily prove the following result. Let X be a class of graphs, K a natural number, F a Boolean function of K variables, and Y1, Yk classes of graphs, each of which admits an implicit representation. If every graph in X is an F function of graphs H1, Hk from classes Y1, Yk respectively, then X also admits an implicit representation. From the structural characterization of quasi-chain graphs presented earlier, we know that any quasi-chain graph is a function of a chain graph and the graph of vertex degree at most 2. Chain graphs have bounded click width and therefore admit an implicit representation, and any class of graphs of bounded vertex degree also admits an implicit representation. Therefore, the class of quasi-chain graphs admits an implicit representation too. One more positive result that has been derived from the structural characterization for quasi-chain graphs presented earlier deals with the independent dominating set problem. This problem asks to find in a graph an independent set which is maximal with respect to set inclusion and is minimum with respect to size. This is a very difficult problem which is NP-complete for general graphs, and moreover it remains NP-complete in many restricted graph families. In particular, it is NP-complete for two P3 free graphs, because this class contains, as a subclass, the class of so-called SAT graphs, where SAT graphs stand for satisfiability graphs. This is a class of graphs where the independent dominated set problem coincides with the satisfiability problem. The independent dominated set problem is also NP-complete for bipartite graphs and even ordinal bipartite graphs. And now we show that the problem admits a polynomial time solution in the intersection of these two classes, and even more generally in the class of quasi-chain graphs. A solution is based on a technical lemma which states the following. A quasi-chain graph G with n vertices contains a collection phi of big O of n subsets of vertices that can be found in polynomial time, such that every subset F in this collection induces a graph of degree at most 1, and every independent set in the graph G is contained in one of these subsets. With the help of this lemma, the polynomial time solvability of the independent dominated set problem in the class of quasi-chain graphs can be proved in the following way. From this lemma, we know that an optimal solution to the problem is contained in one of the subsets of the collection phi. So we inspect each of these subsets one by one. Each of them induces a graph of simple structure, a graph of degree at most 1. Therefore, all maximal independent sets in the subgraph of G induced by a subset F in this collection have the same size. All maximal independent sets in this subgraph contain all isolated vertices and exactly one vertex from each of the edges. Therefore, all we have to do is to show that in polynomial time we can determine whether F contains a maximal independent set which is also maximal in the graph G, meaning a maximal independent set dominating the graph G. Without loss of generality, we may assume that the set F itself dominates G, because otherwise no subset of F dominates G. We denote the vertices of degree 1 in F by F prime, the vertices of degree 0 by F in F by F double prime. We also denote by A double prime and B double prime the vertices in the A part and in the B part respectively, which are dominated by some vertices in F double prime. Finally, we denote the remaining vertices of the graph by A prime and B prime. According to our assumption, these vertices in A prime and B prime are dominated by some vertices in F prime. Now let's look at the subgraph of our graph G, induced by the vertices of A prime restricted to the part A, Fa prime, and the subset B prime. The subgraph of G induced by these two sets is bipartite, and I claim that it is 2k23, because otherwise a 2k2 between these two parts, together with some edges between these two parts, would create a 2p3, which is forbidden. So since this graph is 2k23, meaning a chain graph, we conclude that Fa prime contains a vertex that dominates B prime. Similarly, Fb prime contains a vertex which dominates A prime. And therefore, the set F contains a solution if and only if Fa prime and Fb prime contain two non-adjacent vertices that dominate A prime and B prime, which is easily checked, can be easily checked, and which concludes the proof of this theorem. We also proved that the maximum edge by click and balanced by click problems can be solved in polynomial time for quasi-chain graphs. And note that both problems are NP-complete for general bipartite graphs. There is a number of other algorithmic problems that are NP-complete for general bipartite graphs: Hamiltonian cycle, maximum induced matching, alternating cycle free matching, minimum dominating set, Steiner tree, and the status of all these problems in the class of quasi-chain graphs remains open. With this open problem, I conclude my talk, and thank you very much for your attention.